Hey everyone, welcome to the pilot episode of Read AI with me. In this series of videos, I'm going to be walking through with annotation about some of the papers that I really like in the field of artificial intelligence. Specifically, the first paper we're going to read is in the field of explainable AI. So, hopefully this will be interesting for you. And if I make a mistake, let me know in the comments and we'll get a correction video posted and then we can get this chain effect going. So, with that being said, let's turn our attention to the iPad. Now, this paper that I'm reading today has a very exotic title. Why should I trust you, right? And it's specifically talking about explanation on the predictions of any classifier. So, right off the bat, I think this any is going to be the keyword that me personally like very much, right? If we're going to be talking about some methodology to explain some predictions, I would want to work with as many classifiers as I possibly can, right? If you're gonna give me some deep learning methodology that's making some predictions and it worked great, but then I turn to some other methodology such as support vector machine or random forest, it stopped working. That's not gonna be good. That's not gonna be cool, which is why right off the bat, I think this title has its own catchiness going on. So right off the bat, I know this paper is going to be something interesting. First of all, let's read the abstract. Despite the widespread adoption, machine learning models remain mostly black box. So black box, that's going to be the first keywords that's taking some of our attention, right? In other words, they're really trying to inject trust, the worthiness, into making predictions. So that's going to be the sell, that's going to be the motivation, and specifically they're proposing this methodology called LINE. And it's a novel explanation technique that explains the predictions of any classifier in an interpretable and faithful manner. So I think the keyword here is interpretable and faithful manner. Specifically, by learning an interpretable model locally around the prediction. So there are a couple of things here to pay attention to. First is, as I said in the beginning, this methodology works for any classifier. So give me some black box model, maybe I don't really know what's going on in the model, but hey, that's okay. This proposed methodology line can maybe help us gain some insight of what's going on and how this black box model make its prediction. So that's number one. Number two to pay attention to is this word local. So I'm not really trying to say that, oh, this is going to be important and I'm done. More specifically, what's interesting about this methodology is they're able to pinpoint exactly the local impact that the feature has on the overall prediction. So if there's a picture and there's an area that's important, then what they're trying to say is, if I move away from this area, then I don't really know what's going on. And I think that sort of philosophy provides some good insight, right? If I see this picture, it's my father, and his face is in the center of the picture, then by definition, if I move away from the center of the picture, I shouldn't be able to tell that this person is my father. So this local idea that this paper is trying to sell is going to be the second important thing that I really like. Let's keep going. They also propose a method to explain models presenting representative individual predictions and their explanations in a non-redundant way, framing the task as submodular optimization problem. And they demonstrate the flexibility of these methods by explaining different models for text and image classification. So, we get to see a couple of applications here. That's why I like this. Me personally, most of my research as of right now handling image classification. So I think I would want to focus on that just for my own sake. Now, of course, if you're curious, you can focus on text as well. And then they land on the following, right? They show the utilities of the exploitations via novel experiments, both simulated as well as human subjects, on a variety of scenarios that require trust. So once again, this buzzword trust, which they actually give some sort of definition, right? This column here that we're looking at in the end of this abstract paragraph, which is to say, deciding if one should trust a prediction choosing between models, improving an untrustworthy classifier, and identifying why a classifier should not be trusted. So really, in other words, what they're really trying to sell here is to make this tie between trust, which is, in my book, something quite difficult to define, and the methodology that they provided, which is line. And this paper is really to make that connection. So I think right off the bat, that's a good sell. Let's read the introduction paragraph. Machine learning is at the core many recent advances in science and technology. Unfortunately, that's going to be the motivation. The important role of humans is an oft overlooked aspect in the field. Now, I don't necessarily think that's true, to be honest. From my experience working in industry, in finance, in a Eurostock 50 company, I don't really think that humans in humans' role are overlooked. Um, I do believe that we are really trying hard to understand what's going on, and we're really trying hard to understand what's inside of a model. And if we can't understand that, then chances are you're not going to get that product pushed to the marketing people. You're not going to get that product pushed to the investors, and there's not going to be a sale. So I do believe in the industry, there are a good amount of effort, more than you know, to really push the understanding of the black box models. They're not just, oh yeah, we have a prediction and we're done. So I do believe this sentence is maybe a little bit too harsh, but hey, they're writing a paper, so they're really trying to make a sell. So let's stick with it. Whether humans are directly using machine learning classifier as the tools or are deploying models within other products, a vital concern remains. Okay, the vital concern, that's going to be a motivation. If the users do not trust a model or a prediction, they will not use it. That's of course true, right? If I don't trust this, why the hell do I want to use it? It is important to differentiate between two different but related definitions of trust. So to talk about trust, they are saying that we need to talk about two things. The first thing is trusting a prediction. And what that means is whether a user trusts an individual prediction sufficiently to take some action based on it, right? It's like I buy a stock and my AI algorithm tells me, oh yeah, today at 10 a.m. you should buy 100 shares of Apple. Okay, um, that's a prediction, and it's coming from a black box model. Am I really gonna act on it? Am I gonna open up my account, press the button, and buy 100 shares Apple? It's difficult to say. I've been in the field for many, many years, and based on my experience, I don't think the number is more than 10% to just blindly trust prediction. Oftentimes, what I do is I do a lot of back testing, and even if I want to act on a prediction coming out of artificial intelligence, I put a stop loss order on that initiation, which means if things go wrong, I have an exit. That's going to be how actions are executed in real world. And I do believe they brought up an important opinion on the table. Whether that consists of the definition of trust, specifically in artificial intelligence, that's a separate argument, that's a separate debate. But I do believe this number one problem that they're trying to bring on the table is indeed very important. So let's keep going. Number two, trusting a model. Trusting a model, what is that? Whether the user trusts a model to behave in reasonable ways if deployed. Now, it sounds a mouthful. It sounds like they're really trying to talk about the same thing, but like two sides of a coin. I think the interpretation here is the keyword model versus the keyword prediction. Prediction is saying, oh yeah, you should buy Apple today. Okay, that's a prediction. It's a good buy. AI have this recommendation. That's a prediction. Trusting a prediction is a separate story. It's a separate research than saying trusting the model. Trusting the model is saying because we look at the financials, because it has good earnings, because from the forecast next year, Apple is gonna go up 50%. And then there's some sort of prediction. Oh yeah, therefore today you have to buy Apple. Now, that's of course some random example that I just drop on the table. It may or may not be valid, but I think the model here is really about the decision-making process to search for that decision rule versus a prediction is an action recommended by AI. So I think if you want to break the trust into these two components, it's as if you're saying that the trust is dependent on the order of when you read the algorithms, right? Let me draw a small map. Say you have your data X and then you have some training label Y, and altogether you search for a black box model F. This is going to be black box. And then this black box is good. Say you're happy with the results. Then what's happening is you give a new data, you send it into this black box, and then it gives you some predictions. So in other words, this stage number 1, you can call that research. And then the stage number 2, you can call that deployment. So in other words, so the paper is really trying to bring up people's attention of this understanding of trust is really based on how you trust the prediction, this Y hat, or how you trust the model, this F, right? This mapping, this decision-making rules. So me personally, I think they're good and bad about this. Now, the first thing, let's say something good about this. It's straightforward. It's a mental map that's clear. And that's the process. That's how we deploy a model in real world. If we can trust every step of this process of how to deploy a model, sure, you can claim there's trust there. That's great. And in terms of machine learning point of view, in terms of artificial intelligence, computer science, I do believe that if you can fully explain these two blue boxes, you should be able to establish some sort of trust. But the key point here that I think they're missing is audience. So let's put up a keyword here, audience. The assumption here is whatever deployment of AI, whatever this F is talking about, whatever this Y hat is talking about, the audience has the understanding to interpret what these things are. The audience has the knowledge. If you give them an explanation, they can understand what this is talking about. The audience has the capability in education to understand, okay, if I tell you what is this Y hat, then they know what this Y hat is. Now, in terms of actual practice, that's not always true, right? Say I have an AI, very fancy, right? Advancedly built, that is extremely accurate, right? It predicts tomorrow's stock price with as little error as possible. Is it going to be a successful sell and I'm just going to start making billions of dollars? That's of course not going to be true, right? The reason is because the investors are not going to understand why the successful prediction of tomorrow's stock price can guarantee making you money. And that's going to be the key component here, which is this audience. From experience, I don't really think that audience has the full capacity and education level to understand these two things. And that's going to be important. And that's going to be a roadblock. Now, we haven't really talked about the entire paper yet, right? Maybe they talk about this part, maybe not. But right off the bat, I do believe that you need some sort of education level to fully understand this paper, right? It's not like every high school student can just magically understand this paper. I don't even fully understand it. I'm still trying to learn as much as I can. So this audience component is something that I believe is not emphasized in the context of this paper, especially when they're trying to say this concept of this trust here. The audience component is not really mentioned. So let's keep going. Determining the trust in individual predictions is an important problem. Yes, that's true. When using machine learning in medical diagnosis or terrorism detection, for example, predictions cannot be acted upon on blind faith. That's of course true, right? You don't want to just send your army and troops, we're talking about human lives, into Iraq without understanding what algorithms are doing, right? You can't just be like, yeah, hey, take some AK-47s, go to Iraq, and just start shooting, right? That's not going to happen, right? That's not how we make rules here. Apart from trusting individual predictions, there's also a need to evaluate the model as a whole before deploying it in the wild. Yeah, that's exactly true. We talked about that. To make this decision, users need to be confident that the model will perform well on real-world data according to the metrics of interest. Okay, so if you say that this metrics of interest has some sort of audience component in it, then I think that's a connection that we can make, right? I don't know if this paper is going for that direction, but I do believe this metrics of interest is related to audience. So here we're going to say related to audience, and we're going to put it here. Currently, models are evaluated using accuracy metrics on an available validation dataset. However, real-world data is often significantly different. And further, the evaluation metric may not be indicative of the product's goal. So this is absolutely true. Textbook doesn't mean real world. I 100% agree with that. Inspecting individual predictions and their explanations is a worthwhile solution. Okay, so I think the key point here of why they're talking about individual predictions is really trying to tie up of this concept of local predictions that they're trying to do. Now, I already read the paper, right? That's why I have some understanding why they're making this connection. It's because Lime is really looking at the instance-wise explanation. And we're going to get into the algorithm to see how they did it, but I think that's why they're really trying to draw this connection, right? You have AI making predictions, right? Then you have this field, XAI, trying to explain the predictions. And there are a couple of perspectives, right? The perspective that they're taking is a local explanation. So I think this is going to be important for them to point this out, at least for an audience like me. I'm new to this, right? I don't really know what they're doing. I don't really know how many years they're doing. I don't have that experience. I don't have that expertise. Great. That's the kind of information that it's good to emphasize. Okay, so let's keep going. In this case, it's important to aid users by suggesting which instances to inspect. Okay, that's also tied up to their central theme, especially for large datasets. Okay, that's great. In this paper, they propose the following. Explanations for individual predictions as a solution to the trusting prediction problem, and selecting multiple such predictions as a solution to the trusting model problem. It's kind of mouthful to read trusting model twice in one sentence. But then if you look carefully, which I think I missed, is prediction and model. So that's going to be the difference, which tied up to what they're talking about here. That's the difference. Okay, so let's take a look. Number one contribution, line. An algorithm that explains the predictions of any classifier or regressor in a faithful way by approximating locally with an interpretable model. And I think there are a couple of implementations online saying interpretable as, even as simply as linear regression, right? I've seen people end up using that in line as an adaptation to the proposed methodology in this paper. Me personally, I think you can go a little bit more difficult and complex than linear models. But, that's just what people do online. Let's take a look at this paper. And then they're also second, right? SP line, okay? And then another thing that they're saying is comprehensive evaluation with simulated and human subjects, where we measure the impact of explanations on trust and associated tasks. In our experiments, non-experts using LIME are able to pick which classifier from a pair generalizes better in the real world. Further, they're able to greatly improve an untrustworthy classifier trained on 20 news groups by doing feature engineering using LIME. Okay, so this entire area is talking about audience. Okay, so yes, the answer to my previous confusion in the beginning of reading this paper is they did talk about audience, right? And specifically, they say that they have non-experts. Meaning what? Meaning this map that I draw here, this component, and the question specifically being, can the audience understand these two things? Presumably, if my understanding is correct, and when they're using non-experts, they're talking about regular people like you and me. And hey, if they understand it, then hopefully we can also understand it, right? So that's gonna be great. Okay, let's keep going. By explaining a prediction, we mean presenting textual or visual artifacts that provide qualitative understanding of the relationship between the instance's components. Words, patches of images, whatever, right? And the model's prediction. We argue that explaining predictions is an important aspect, getting humans to trust and to use machine learning effectively, if the explanations are faithful and intelligible. The process of explaining individual predictions is illustrated in figure 1. So figure 1 is here, that's figure 1. Let's read the paragraph first and then let's go to figure 1. It is clear that a doctor is much better positioned to make a decision with the help of a model if intelligible explanations are provided. In this case, an explanation is a small list of symptoms with relative weights, symptoms that either contribute to the prediction or are evidence against it. So the contribution, they're going to put it in green, and uh, the ones that are not helpful are against it, they put it in red. And then they're saying humans usually have prior knowledge about the application domain which they can use to accept or trust or reject the prediction if they understand the reasoning behind it. It has been observed, for example, that providing explanations can increase the acceptance of a movie recommendation or some other automated systems, right? So with that being said, let's take a look at this. Okay, maybe we're getting somewhere. Here you have a model, right? Let's say you have some sort of black box model, this F. It could be a neural network. It looks like what they're drawing here. It's a neural network. And essentially, you have a couple of things here. These features, you can call that X. And this flu, it's an outcome, right? It's dependent on the features. So yeah, you can say that's something that you want to predict. So you have Y. Give me this X, give me this Y, and then give me this black box model. Then what Lime is doing, this is what they propose. So this paper, this is what they propose. It's really trying to say, okay, the predictions that this person has flu is coming from the features that are whether this person sneezes or not, right? So sneeze. Weight, maybe not that important. So Lime says, hey, maybe we drop that. And then what else? Headache. Headache is an important feature too, right? If you have headache, then chances are you might have flu. Okay? So no fatigue. Okay, that's another one. But then it says no fatigue. So if you're contributing to whether this person has flu or not, it should really be the opposite of no fatigue. So you have fatigue. So in other words, this is green, that's sneeze. Headache, that's green. And the fatigue, the no fatigue, it's red. And that's really what they're trying to infer by this explanation used by Lime. And that's the roadmap that they're trying to do. So if I may, which I don't think is mentioned in this paper, I think that the figure 1, just by reading the figure 1 itself, not reading the rest of the paper, I think the key here is really about feature selection. So if I may, I think I can say feature selection. And I think that's really the key here. I think it's interesting to see how they're going to carry out feature selection, even though they didn't really mention the word. But I do believe this is a feature selection problem, right? Let's say you have this is x1 is sneeze, x2 is weight, x3 is headache, x4 is fatigue or not, x5 is age, right? And then I'm making this prediction. And then after all this work is done, Lime is coming here and say, okay, let's look at the model, right? Let's look at the features. Let's look at the outcome variable. Okay, this x2 weight it's not that important. Let's cross that. Age is not that important. Let's omit that. And we're left with these three variables, which being x1, that's sneeze, x3, that's headache, and then x4, fatigue or not. So in other words, if I may, I think the key here is about feature selection, and specifically how these features influence or impact or change the outcome variable under the assumption that this F is the black box algorithm that the prediction has been using. So really that's the gap here that we're trying to fill. And specifically, for the sake of time, I want to focus on the first methodology. So let's go ahead and talk about this part first. I think this part is quite interesting. It talks about the desired characteristics for explainers. So let's take a look at that. We now outline a number of desired characteristics from explanation methods, right? So recall the big gap, right? We have our data, we have our dependent variable, we have this black box model. Now, this proposed method line is trying to explain it. And what do you mean by explain it, right? Well, they are talking about it right now. So, an essential criterion for explanations is that they must be interpretable. Okay, so let's highlight that word. What does it mean, interpretable? So here you can actually say definition, right? What does it mean, interpretable? Well, definition is here. Provide qualitative understanding between the input variables and the response. Now, I think this definition of interpretable, it's a little bit vaguely defined. There's another survey paper that talks about the difference of interpretability and explainability. So if I dare, let me write here, interpretability and explainability, which is actually related to introvert and extrovert in a linguistic point of view. Now, me personally, I'm not a linguistic, right? I don't really know how to judge that part of the connection that these other paper is making, but I do believe there's a slight intrinsic difference between the word interpretation and explanation. However, the definition given in this paper, right, this provide qualitative understanding between input variables and response. This statement can actually be used both on interpretability and explainability. So in other words, the proposed methodology line, whatever it is, we're going to get into that, whether that serves as a differentiation of interpretation and explanation, I don't believe that's discussed in depth in this paper. So, in other words, what I'm really trying to get at is this qualitative understanding requires a little bit more rigorous definition or description of truly what you mean by interpretation. And unfortunately, I don't really think that's well defined in the literature. Maybe if you find it, you can share it with me. I'd love to read that paper. But then on the upside, I'm glad that this is mentioned. So that's definitely going to be some credits that I need to give to them, because without this statement, we don't really have a start. So that's that. And then let's keep going. We note that interpretability must take into account of the user's limitation. Thus, a linear model, gradient vector, additive model may or may not be interpretable. That's of course true. I agree with that. For example, if hundreds or thousands of features significantly contribute to a prediction, it is not reasonable to expect any user to comprehend why the prediction was made, even if individual weights can be inspected. This requirement further implies that explanations should be easy to understand, which is not necessarily true of the features used by the model. And thus, the input variables in the explanations may need to be different than the features. Finally, we note that the notion of interpretability also depends on the target audience. Aha! This is the keyword that I've been looking for. This audience is going to be extremely important, right? Without the understanding of who your audience are, you don't really know what's the right language that you should use. So I'm actually very glad that they talk about this part, and I think it's extremely important. Machine learning practitioners may be able to interpret small Bayesian networks, but laymen may be more comfortable with a small number of weighted features as explanation. I like that they're mentioning Bayesian networks. Um, I've actually spent a lot of time, and I don't even think I fully understand Bayesian networks, so that's going to be a small dinner table joke, and I'll definitely keep that in mind. Another essential criteria is local fidelity. This is going to be something extremely important. Right? First thing, it talks about local. That's going to be the buzzword for their paper, and then it talks about trust, right? Fidelity or fidelity. So these two words serve as local fidelity. Although it is often impossible for an explanation to be completely faithful unless it is complete description of the model itself. For an explanation to be meaningful, it must at least be locally faithful. Great, that's the keyword I'm looking for. It must correspond to how the model behaves in the vicinity of the instance being predicted. And again, this is local, so we're going to say local. We know that local fidelity does not imply global fidelity. That's true. They're giving themselves a way out. Features that are globally important may not be important in the local context, and vice versa. That's true. While global fidelity would imply local fidelity, identifying global faithful explanations that are interpretable remains a challenge for complex models. True, I agree with that. While there are models that are inherently interpretable, an explainer should be able to explain any model and thus be model agnostic. And model agnostic is just another buzzword when people want to say, okay, this thing can work for any model, right? Any classifier. So if something being model agnostic, I think it's good. I think it's definitely good. It means that it's flexible and it doesn't really constrain itself for one algorithms. And I think that's great. If you are in the field and you may be aware of a technology called CAM, so that's going to be short for Class Activation Map. This CAM is also used widely in XAI literature, and one issue with CAM is it's specifically taken the last convolution layer of CNN. And basically what that means is if I have a model that's not CNN, okay, then CAM should probably not be your candidate to go. So I've gone through that trouble myself, and I've handled the situation where the approaches are not model agnostic, and I've gone through the pain. So I can tell you guys that if you see something that's model agnostic, there are more options for that approach, which by itself innately is an upside. Apart from the fact that many state-of-art classifiers are not currently interpretable, this also provides flexibility to explain future classifiers. So that's the part I just mentioned. In addition to explaining predictions, providing a global perspective is important to a certain trust in the model. As mentioned before, accuracy may often not be a suitable metric to evaluate the model, and thus we want to explain the model. So all that sounds good, but we talked a lot about the background, the introduction, why they sell this paper, what is the motivation. So now I want to get into the actual algorithm of the model, and for the sake of time, I'm just going to cover the first contribution, which is line. So here we're going to focus on line. LIME is short for Local Interpretable Model Agnostic Explanation. And the overall goal is to identify an interpretable model over the interpretable representation that is locally faithful to the classifier. So that's going to be something great. And specifically, the keywords here that mentioned a lot in this paper is interpretable representation. And here mentioned again, for example, here's in image text classification, or likewise for image classification, they're also looking for interpretable representations. And something like that, it's extremely interesting. Here, this algorithm start with some sort of a model G, right? Neural network, random forest, whatever, right? There's going to be a model G. And it could be potentially interpretable, but it doesn't have to, right? Some G, okay? And here, there's some sort of a domain, right, which is defined over this 0, 1 in dimension d prime. And then essentially the G acts as an absence or presence of the interpretable components. But the model here being explained throughout the process can be defined as this F, which could be from some sort of d-dimensional data all the way to some sort of output, which is could be a single value, or it could be some sort of a class, which is in R. And finally, there's this concept of this pi x as a proximity measure between the instance z to x. This is sort of like a distance function, right? And the one thing to mention is this loss function. So this loss function taking the input of your model, right? This f being explained, and then your g, the original model, the black box model, and also this pi x. And this pi x later on they define it as this kernel function, and not just any kernel function. It's the exponential kernel function, which taken into the form of essentially this exponential function, and then it's being used in formula 2, and this pi is the kernel. And this figure 3 is going to be extremely important, and specifically it talks about the intuition behind line. So let's read this. Figure 3. Toy example to represent the intuition for line. The black box model's complex decision function f, it's unknown, is represented by the blue-pink background. So in other words, whatever this f is, we assume that we don't know that. We don't have the access to the internal structure of this f. And what that means is, however, it's making this rule, it doesn't matter. We're just going to draw this area as the decision-making boundary, right? It's within this area. If it's within this area, it's one class. If it's outside of this area, it's another class, right? It's a set of rules. We don't know how the rules are made. That's it. That's what we're working with. And then what's happening? The bold red cross is the instance being explained, which is here, right? So we're going to mark it. That's the dot, right? It's an observation. We want to explain that, right? We want to see what's going on. Line samples these instances, gets prediction using f. So in other words, we have this dot here, and given this dot, we have features, and give me this f, we have a prediction, right? So in other words, for this I as this dot, and I can take a look as yi hat by some sort of function f, give me all the features x. And this yi hat can be some sort of prediction, right? If the picture is cat, then I want to know what's the probability that this observation is a cat. So that's going to be coming from the educated guess of this black box model f. And then the line weighs them by the proximity of the instance being explained, which is represented here by the size. So in other words, what they're trying to say here is, imagine there is a dotted circle that looks like that, and this dotted circle can get bigger and bigger, right? And if another instance is closer to the red dot, meaning it could be in a smaller blue dotted circle, then this distance is going to be smaller. Then they use this bigger plus sign to measure and indicate that these two dots are probably closer to each other, maybe have the same features, right? If something is further apart, right, maybe an instance is there, and that's the distance, right? Obviously, D1 is smaller than D2, right? And that dot is measured by the smaller plus sign, right? A smaller plus sign. And that basically means your your instance there is further apart from this target instance, and maybe the features are starting to get a little bit different, right? It maybe look different apart from each other. Then perhaps the intuition is okay. It might have a different prediction, right? This y I hat might be very different. Now, hopefully, this y I hat here for uh, the triangle guy, which is here, is going to be a closer estimate with the target than this square guy. This is a square, this is a triangle. So hopefully the triangle is closer to the red target. That maybe it has a closer educated guess by the model. The square, which is here, is further apart from the target instance. Maybe it looks different. Then the model might give a different educated guess simply because they're further apart. So that's really the key here that Lime is trying to exploit, right? And in the end, we say the dashed line is the learned explanation that is locally but not globally faithful. Where's the dashed line? The dashed line is here. That's the dashed line. Okay? And that line pretty much says, okay, by looking at all these instances, right? Maybe the instance is sampled there, maybe it's 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 there. Doesn't matter. We're looking at all these instances, right? And it doesn't matter where it goes, right? It could be here, it could be here, it could be here, it could be here. It's surrounding this target instance, right? Ideally, the closer it gets, the same educated guess it will have. But then, how do you draw this green line? It's because when you happen to be on this side of the area, the right-hand side of this green line, the prediction is another class. And then if you're on the left-hand side of an area, the prediction is another class. So maybe we say left is class 1, and then right is class 2. And it happened to be the case that this dotted line separate the boundaries. And if you watch closely, whatever this shape is, this dotted line perhaps is exactly the tangent of the shape, which is the decision-making rule at that instance. And that's really how Lime investigates what's going on locally at this instance and how this point consists of features that contributes to the final prediction, y hat, that's coming out of this black box algorithm F. And what I just said, it's nicely described in this algorithm number 1, which essentially is Lime. You require your model, you require an instance, right? That could be your training set, right? So here we're going to say train. And then obviously, there's an interpretable version, which may be a subset of the features, right? The sneeze is going to be important when you're trying to identify flu. The age is probably not going to be helpful. So that's the second thing you require. And then the third thing you require is this kernel function, right? Remember we talked about the exponential kernel function. Here we're going to say this is the exponential kernel function. And altogether, you run through this algorithm. Each step, you go through each of the instance and you sample around the instance that you like, the target instance, and then you collect this z, which is defined by the union of these two things, right? This is the model, this is the kernel, and z is the sampled instances around the target instance. Altogether, each step you update your w. And how they update the W is using a lasso function, which is another machine learning algorithm in your machine learning 101 that everybody studies. Essentially, they come up with sets of weights, and the weights tell us how each X is affecting the prediction of Y. And end of the day, this W is what we're interested in, right? It pretty much tells us the direction of where you should go, right? If you have this instance, if you move away from a target, then maybe the educated guess is far away. It's very different. If you're close to a target, maybe it's the same. But then on top of that, the proximity is going to be one thing. So let's write it down, proximity. And then another thing is going to be the sign. sign is also going to be important, right? If it's a classification problem, maybe sometimes it's close to each other, but it happened to be the other end of a line, right? Maybe sometimes you are close, but then you cross this line, then your sign is going to change. Then that gives you a different class. Then it gives you a different label class on your instance. So something like that is quite interesting, right? In this paper overall, I think what's really catching my eye is its capability of explaining locally what's going on given any black box algorithms and how they affect the prediction. So there you go. I hope you enjoyed this pilot episode. If you like the channel, give it a like and click that subscribe button. If you still have questions, if you want to read more papers, leave a comment, let me know, and I'm happy to get to it. With that being said, have a good day, and I'll see you in the next episode.